Here we go. All right. So once again, structure of blood vessels. We have three major categories. We've got our arteries, we have veins, and our capillaries. And I have it laid out kind of like this, where you start in the top left corner and you follow this down, and then you kind of loop around underneath and then go back up to the larger veins in terms of blood flow trajectory. So if we're blood that's immediately leaving the heart, going out into our systemic circuit, we're going to start in our elastic arteries, right? So the elastic arteries are the biggest vessels that we have in our body that carry blood. And they have each of these three layers that we call tunics. And so you've seen this term before when we talked about the vasculature and layers of tissue that make up the eye. It's the same idea here. We use that word tunic instead. Now it's tunica, but it's the same idea. So we have the tunica adventitia, we have the tunica media, and the tunica intima. All right, so those are our three layers. So the adventitia sits most superficially, media is in the middle, and then intima is the deepest layer of these tissues. Generally, the adventitia is composed of collagen and elastin, so those protein fibers that make up things like tendons. We use a similar configuration of that to make up this outer layer of our vessels. Let's make sure we get Liz and Pam in here. All right, let me pause really quick so that I can get attendance here. Hey, Liz. Hey, Pam. Welcome. There we go. All right, cool. So yeah, once again, those three layers of tissue that make up our vessels. So we've got our tunica adventitia that makes up the most superficial layer. And then we've got the media. So the tunica media, this is where we get some variation, especially amongst arteries, but not so much amongst veins. But the media can vary in muscle composition. So this is where we have the smooth muscle that makes up kind of the tension component of the vessel, right? So this will be important when we talk about things like arterial pressure, mean arterial pressure, and things that can affect, like hypertension or heart or contribute to developing heart disease can all be kind of focused around this tunica media, and then also to an extent the tunica intima as well. All right. Hey, Marnay, welcome.
Hello.
Good to see you. All right. So, so the tunica media, depending on the vessel, can vary in how much smooth muscle it has and how much collagen it has. And these elastic arteries, it's a lot of actually both. It's kind of roughly a 50-50 mixture of collagen and elastin fibers mixed in with smooth muscle tissue. But the tunica media layer is what contributes to the vessel's ability to do what we call vasoconstrict, or tighten or close up on itself. And then vasodilate, where the vessel can open up, right? So very similar to the activity of like your pupils. When you go into a really bright room, they constrict. It's the same idea with our blood vessels. We can change their diameter depending on the need for it. So, there's a bunch of different reasons why you would want to do that too. And then we've got at the deepest layer that makes up what we call the inner and outer lumen, or the inner and outer layers of the inner vessel or the inner tube, is what we call the tunica intima. So the tunica intima is composed of a layer of collagen tissue and then this basement membrane connected to a single layer of endothelial cells. So those endothelial cells will be pretty much all that makes up our capillaries, which is what we'll see in a second. But those two things, so collagen and then endothelia, make up the deepest layer of our vessels, right? So those three layers, intima, media, and adventitia, going from deep to superficial, make up our blood vessels. And depending on the compositions of each of those, that'll kind of determine what vessel we're in, right? So moving into our muscular arteries, so let's say, again, we're in a blood vessel that is moving away from the heart. The first structure, like for example, the thoracic aorta or the dorsal aorta, that would be considered an elastic artery. It's a very large diameter artery. But then as we start to branch off of that and we get into some of these more specialized arteries, then we get into our muscular arteries. So generally, as we get to things like skeletal muscle, we have arteries that are branching off from the main elastic ones that then become what we call muscular arteries. So the muscular arteries, which is probably no surprise, the adventitia layer tends to be a little bit thicker, but the biggest difference is that the media layer is mostly smooth muscle. It's mostly smooth muscle that makes up the muscular artery. It's not necessarily contingent upon whether or not they're actually going to skeletal muscles, because you can obviously have muscular arteries that are branching off that are going to, different kinds of organs like the lungs or the liver or things like that. But the tunica media inside of muscular arteries is going to be mostly smooth muscle at that point. You can even see that in here, that layer is pretty much entirely smooth muscle. You still have your elastic tissue that surrounds it, but it's mostly smooth muscle. And then the tunica intima starts to get a little bit thinner, right? So our collagen and connective tissue that makes up this outer component starts to get a little bit thinner, and the vessels start to shrink and decrease in diameter as we move from elastic artery to muscular artery. So then as we go from muscular artery down to kind of our penultimate level before capillaries, we have what are called arterioles. So these are the literal basic bare bones structure of an artery. These are the smallest arteries that we have that are not considered capillaries. So they've got the tunica adventitia, they have the tunica media, and then the tunica intima. So the tunica intima is pretty much, doesn't have any connective tissue. It's literally just those endothelial cells that are making it up, right? And then the thickness of the media and the adventitia is much more reduced compared to our muscular or elastic arteries. And then finally, we get down to our capillary beds, right? So pretty much any target structure or any tissue that we have in our body where blood needs to go is going to get to that tissue via arteries. And then we have capillary beds that perfuse most of our organs in our body, right? These capillary beds are nice because they provide a vascular connection between our tissues and our circulatory system. But most importantly, the thickness of our capillaries right here is the smallest and thinnest that they can be. It's very similar to the alveoli in the lungs. So the endothelial cells that make up capillaries are literally a single squamous cell thick. It's the smallest barrier to diffusion that we can generate without just having it be an open, structure and there not being any vessel at all. So those endothelial cells that make up the walls of the capillaries are important for just that. They provide the smallest barrier to diffusion so we can transport nutrients and oxygen out of our circulatory system and then simultaneously take up extra nitrogenous waste, dissolved gases that are waste products. We can also even return a lot of our water that makes up our blood as well. So we'll talk a little bit about that capillary exchange later, but capillaries by design, very, very thin, very small, single layer, single squamous cell thick. And again, that's significant because it provides the smallest barrier to diffusion for nutrient transport and nutrient exchange with our tissues. So now we're in our circulatory system. We've passed through the capillaries. And at this point, what's kind of interesting too is blood pressure is essentially zero after a capillary bed. And so we'll kind of think about that as we go along here, why in our elastic arteries appears blood pressure greatest, and why pretty much after a capillary bed, once we get out into a venule, right, and going back up to the heart via the venule, small and medium veins, and then large veins, why blood pressure is essentially zero in these structures. So kind of think about that as we're going through here. So the tunica intima in the venules is pretty much all that makes up the returning vessel that immediately exits the capillary bed. It's basically just the next stage up that you can get from a capillary, right? So we've got some extra collagen that surrounds those endothelial cells, giving you a little bit more support, allowing for these vessels to kind of expand and increase their diameter as they need to. But then as we get closer and closer back to the heart, the vessels themselves are going to have more smooth muscle associated with them, more tunica adventitia. The tunica intima pretty much stays the same between small and medium veins. But then as we get closer to the heart, we get more and more smooth muscle there, right? So kind of pulling a Quentin Tarantino here, and spoiling a little bit about the ending before we get to it. So one thing to recognize is that, again, as we pass through the capillary bed, if we're blood and we're passing through here, so we've gone through our capillary system. Once we exit, we don't really have any force that's pushing us through the veins at all anymore. So what we want to think about here is how the heck, if we're a blood cell, if we don't have any force that's pushing us through these vessels, then how the heck are we able to return to the heart if there's no pressure that's forcing us back this way, right? So something to think about as we move forward here. Here we've got a light micrograph of two cross sections, or of a cross section of two different vessels. So on the left-hand side, we have a muscular artery, and then on the right-hand side, we have our larger returning vein, right? So it's fairly obvious, or it should at least be fairly obvious, the difference between these two vessels, right? The tunica media is so much more substantial than our venule. That's in the same level of the body in the artery compared to the vein. Same thing with the tunica adventitia. The adventitia is so much thicker and more developed in the arteries than it is in the veins. All right. So again, a lot of the thickness of our arteries compared to our veins is due to more smooth muscle, more collagen and elastic tissue. And again, one of the reasons you can think about that, or you might be thinking, well, why is that? It has to do with how much pressure is going to be exerted on the walls of the vessel in the artery compared to the vein. Remember, the veins pretty much don't have any blood pressure in them at all. But the arteries are going to be experiencing blood pressure because they're fairly close to the heart, right? They're still in that first bit of our loop before they get to the capillary bed. So they've got to have a little bit more substance to the walls of the vessels so that they don't completely rupture. Obviously, over time, the walls of these vessels can degrade, they can harden, we can lose collagen, we can lose smooth muscle, and then the arteries themselves can rupture and fail over time. Oh my gosh, I can't think of her name. Lucille Ball. That's what I was thinking of. Anybody watch I Love Lucy? Know of I Love Lucy? Yeah, great show. Lucille Ball, her just as a, actress, woman of comedy, CEO, businesswoman, she's super, super badass. I've grown to appreciate her a lot more ever since I got married, because I didn't really know anything about I Love Lucy until I met my wife. She's a huge I Love Lucy fan, and she educated me on a lot about her. But one thing that was kind of crazy is when she was talking about how she died. She actually died from a rupture in the wall of her abdominal artery. So the descending aorta, as it passes down next to the spine, would be called the abdominal aorta, and that thing ruptured, and she had traumatic internal bleeding, and she ended up dying from that. Now, why that was the case is a little bit more complicated. Part of it's due to smoking. Smoking can put increased pressure on the pulmonary system, and as a result can also put increased pressure on the systemic circuit. So the walls of those arteries were getting a lot more force put on them than they would be under normal circumstances. And so over time, with age and with smoking and things like that, the walls of those arteries, degraded until ultimately, with her, they ended up failing. But that's what can end up happening over time. It doesn't always happen, but it can happen, with things like smoking and things like that can put extra stress on the cardiovascular system that doesn't need to be there. Other contributing factors, can include things like clots or thromboses that can develop inside of the vessel that can block and build up pressure in a particular artery. We can also, and we'll talk about this kind of at the end of our lecture today, but something called atherosclerosis, or hardening of the arteries, can have a similar effect to a thrombosis or a clot or plaque buildup that can happen inside of the vessel. But atherosclerosis is different because it builds up inside of the endothelium of the wall of our vessel. And so that's a trickier issue. All right, so kind of moving right along here. Again, as we're passing through our vascular system, we start out in the arteries, we pass the capillary beds, and then we return through the veins. But what's kind of cool is that we've got all these different little mechanisms that can control where blood moves and passes through. So we have these, what we call precapillary sphincters, which are muscles that can constrict and tighten depending on certain kinds of signals like chemical signals or pressure signals, where we can redirect blood flow and deliver it and take it away from a particular site. So in other words, as blood is passing through here, as it's passing by, blood's going to move into this capillary network if it's allowed to. So if these precapillary sphincters are open, then we can do that. But let's say that you go into a fight or flight scenario. Usually what I like to do in a situation like this is I'll have a big book in front of the classroom and I'll slam it down on the desk, right? So everybody jumps and heart rates get going and things like that. But the point of that is to show that with the effect of adrenaline, right, what that can do is that can redirect blood flow, again, acting as a chemical hormonal signal that will cause the constriction of precapillary sphincters inside of organs like our liver, our intestines, our stomach, things like that would normally control blood flow to there. So what we end up doing is we redirect blood flow to our extremities, to our muscles and our appendages to be able to act in a fight or flight scenario. So that's just one example of how things like a chemical receptor can control that. If you have drops in blood pressure, we have special neurons that, again, we talked about in our last chapter called baroreceptors that respond to pressure changes that are put on the walls of the arteries. Hello, here. There we go. So we've got, all different kinds of ways that we can control the flow of blood, but these little sphincter muscles here are what control the direction of flow and whether or not blood can move into a capillary bed, right? And you might be wondering, well, okay, how are we able to control for that? And really it comes down to neurotransmitters, neurons that send, signals there that respond to things like adrenaline, that respond to things like pressure changes. All of those will send different information signals via the nervous system to the brain. And then we can control whether or not these sphincters end up closing or remaining open. It's the same idea too with the smooth muscle of the walls of the vessels as well. We can increase their diameter or constrict their diameter depending on much the same factors. So things like adrenaline, noradrenaline, insulin, glucagon, drops in blood pressure, increases in antidiuretic hormone, things like that. We'll talk about some other hormonal pathways here in a little bit. And those of you guys who've already read the chapter, you know what's coming here. But yeah, so we've got all these cool different ways that we can control the flow of blood in our body. Oops, went too far. So this is a really cool feature of veins. And so when I was in grad school, I was taking vertebrate surgery classes. My attending professor, who's a respiratory physiologist, showed us, he got out this really cool ultrasound machine. It's a military grade ultrasound machine, but they use it. It's like a portable one that you can use as like a vet, and you can use it on animals. It's got all these cool different attachments and stuff. But he did what's called a vasovagal maneuver, where basically if you invert your head or if you invert your body and your blood all rushes to your head, what ends up happening is we have these backflow valves that can open up and do this. But he did and some of you guys may know kids who did this. If you did this as a kid, this is not an attack on you. But I personally knew a kid when I was like a teenager. My mom's best friend, she would come stay with us, and she had a kid who would just have the worst temper tantrums. You guys insert the kid in your lives that you know of that I'm talking about. But he would do this thing where he would get really mad and he would hold his breath and his face would get all red and he'd start shaking. If you guys know of anybody who's done that, you know exactly what I'm talking about. But anyway, the point is he was building up so much pressure in his venous return system that he would end up losing blood flow to his brain and he would pass out. He did it like once or twice that I saw. I was like, what is this kid doing? But anyway, what's kind of cool about our veins is in order to restrict blood return or blood backflow into our venous return system, we have these little valves that can open up. And if there's a drop in pressure or if there's a vasovagal response that happens to your body, if you invert your head, like if you're hanging upside down on the monkey bars or something like that, these valves can open up to prevent blood from flowing backwards in our venous return system. So that's really good, because then we reduce pressure on the capillary beds and we allow for blood to, keep circulating and moving forward in our systemic circuit. So it's kind of cool. So these valves open up if there's a drop in pressure, or if there's some sort of a nervous response that controls or sends a signal to the smooth muscle that surrounds the vein that can kind of mess around with that too. So all different kinds of ways that we can help reduce blood backflow, because blood backflow is bad because if blood pools and if it sits, then we form clots, we can form emboli, we can form thromboses, all kinds of things. Ooh, yeah, Liz, that's a good question. So is it the same idea when you lock your knees while you're standing? Not quite. It depends on the person. So some people have issues with circulation in their extremities, but oftentimes what can happen, kind of like what you're thinking about here, is like, Liz, I'm assuming that you're talking about like if you stand and you lock your knees for a while, how you like pass out, right? Yeah. So that's a little bit different. You're kind of eliminating blood flow to the brain. So it's a little bit different than closing these valves. You're actually pinching off the entire vessel. So there's just no blood actually getting to the brain. So if that happens for long enough, then yeah, you can pass out. But it would be the same idea if you were a kid and you did the breath holding thing to, prevent blood from getting to your brain, and then you pass out that way. But yeah, so the blood will pool in these vessels. And the neat thing about veins is, since there's really no blood pressure in them, the veins can expand very, very far before there's any kind of structural damage. So in a way, they're a lot more pliable than things like arteries are, which is kind of cool. So Liz, I guess if I'm thinking of your question correctly, it's the same idea. Yeah, like if you hold your breath and you reduce blood flow to your brain, it's the same idea there. But not the same thing as if you like are hanging upside down from monkey bars. You're still getting blood flow to your brain, but the cool thing there is, to prevent blood backflow, these valves can open up so that in these little pockets inside of your veins, you can still maintain the same blood volume, and then your heart can still force blood throughout your body, but it's not getting this like massive influx of blood from the veins into the right atrium. So you'll still get a little bit of an extra volume increase in return. But I think we talked about it last week, but just in case I didn't mention it, on top of the atria, we have these two little extra chambers called auricles that essentially account for changes in blood pressure that go with, us just getting up and moving around and changing our posture throughout the day. If you sit, if you stand, if you lay down, your blood pressure changes all throughout your body. So the auricles that sit on top of the atria can act as these extra bits of volumetric capacity in case there's extra venous return for some reason, but it's not like a massive amount or anything. I know that was a really long-winded answer to your question. So, but thanks for asking that. No worries, Lorenzo, you're good, man. Okay, so thanks, Liz, for your question. Anybody else? Anything else before we move on? Okay. All right, so we're not really going to talk about this diagram too much because you guys have already seen this before. This is, each of our different circuits to our body. So we've got the systemic and pulmonary ones, and then again, the little third branch that's off of the systemic circuit being the coronary, supplies blood to the heart. But this is our general pathway, but this is just highlighting that each of the organs in our body, each of the major tissues that we have, all have capillary beds in them. You wouldn't believe how many capillary beds are all over the place. Places like the kidneys, the intestines, liver, it's insane. The blood network in the brain. We'll look at a couple images here in a sec so you guys can see, some of the major vessels that provide circulation to the brain. It's extensive, right? So every important organ and tissue that you can think of in our body has a rich network of capillaries that are supplying blood and oxygen to those particular tissues to help satisfy their metabolism. So just again, as a quick preface, the easiest way and the easiest way to learn these structures, if you guys haven't spent any time on them yet, if you've completely forgotten all of your regional terms from the beginning of the year, if you've forgotten your bones, that's okay. Just memorize the arteries. all right? Because the veins pretty much have the same names to them, because, and the same thing goes actually for the nervous system, the same thing goes for the lymphatic system for the most part too. You know, you've got your femoral artery that you'll see right here, and the femoral vein is in the same spot. It all runs together. The femoral nerve runs right next to that. The femoral lymphatic duct runs right next to it. It's all the same stuff. And so since it's in that same area, we just use the word femoral, or, you know, femur, to describe that, because this is the femoral region of the body, and the bone that's right next to it is the femur, right? So that's why, you know, remembering those regional terms from the beginning of the year will pay off huge, because, you know, if you remember your areas of the body, then, you know, then it helps you a lot with this. But again, if you didn't, that's okay. I would say just memorize the arteries, because most of the veins have the same names, right? Okay, so what do I want to talk about here? Kind of just like a fun fact, the descending aorta, so this larger vessel you can kind of see that's running down the spine right here, actually has kind of a leftward orientation. So it's not really substantial. It's not like it's all the way, as you can see, it's not like it's all the way on the left side of your body, but it runs down the left side of the vertebral column. So it's kind of an interesting phenomenon where a lot of recovery positions to place like patients in, or if you're, you know, pregnant or anything like that, or if you're, you know, recovering from an injury or something, usually, if possible, it's advised that you lay on your left side for the best recovery position. One of the reasons for that is because it puts less stress on the systemic output system of the cardiovascular system, because the arch of the aorta right here goes up and around and down the left side of the spinal cord right here. So if you're already laying on your left side, the heart doesn't have to force blood against gravity. Like if you're laying on your right side, it doesn't have to force blood up and out. It can just push it out through the aorta, and kind of just let gravity help and assist with the output of that flow. Now, in terms of, you know, whether or not the arterial pressure difference between laying on your left side versus laying on your right side is substantial, I don't know. I don't know what those values are, but there's probably some science to, you know, why most healthcare professionals would recommend that you lay on your left side for some of the best recovery positions. So there's some interesting thought to that. So, and kind of in another way too, we can tend to think of arteries as kind of being left justified in our body, and veins tend to be right justified. So the venous return will end up kind of coming back, in the inferior vena cava and the superior vena cava kind of end up hanging out on the right side of the dorsal aorta right here. So it's kind of cool. All right. So again, here we've got our different arteries that make up, you know, the abdominal and thoracic areas. Again, you'll notice that a lot of them have nomenclature that's related to the vessel that they're supplying, or I'm sorry, their structure that they're supplying, so like the organ or something like that. Some of them have proprietary names, and that's okay. But again, most of them are related to the area or object that they're supplying blood to. So I have a little link right here. So the internal thoracic artery can sometimes be used for a bypass surgery if necessary, right? So this little guy that's running down right here, the internal thoracic artery, can use that in a pinch. If for some reason, you know, the physician doesn't want to use the greater saphenous or the cephalic vein, you can use the internal thoracic artery to help kind of repair or do a bypass surgery. And it's nice because it is literally just right there. All right, let's see. So I have this little bit on aneurysms. Well, I shouldn't say we, but my in-laws lost one of their friends this past year to an aneurysm. And so he had a arterial aneurysm where an artery that was supplying blood to, forget which region of his brain it was, but it ended up swelling and rupturing. And he ended up having a brain bleed, and he ended up passing away from it, which was really, really unfortunate. And but that's just something that can happen with increased blood pressure to arteries that are supplying blood to areas of the brain. If you have a arterial rupture in another part of the body, it's obviously not as detrimental. If you have an arterial rupture in like your arm or something like that, then depending on clotting factors or depending on where the vessel is, it's not really the end of the world. Sometimes if it's a small enough artery, then you can, your body will repair it on its own. You can have a, you can just have a bruise and then it repairs itself on its own. But sometimes if they're bigger arteries, then it's a lot more problematic. And especially if it's around tissue like your brain, where if a clot forms and a hematoma arises, then that can impair the function of that tissue too. So arterial aneurysms, right? Ruptures of the particular vessel due to increased blood pressure or increased blood output through that vessel, and weakening of the walls will cause it to fail. And so here's what I was talking about last week too, where some of these flow charts are really helpful to help you learn and understand where blood is flowing and where it's being supplied to and where it's coming from. It's just a great way to kind of conceptualize where you're at in the body and where you're coming from if you're a red blood cell. So here we've got a bunch of different arteries that make up the blood supply to the brain. Every single one of these little branches has its own name, and each little branch off of that has its own name. So there's several that are not depicted in here, but as mammals, we get a ton of blood supply to our brain. And if we lose blood supply to our brain, then that's really bad. We can't really go for long without blood to our brain or without oxygen being supplied to our brain. But again, really cool animals like alligators can slow their metabolism, redirect blood flow to other organs in their body, like their brain if they need to, but they can last for super long periods of time without breathing. It's fascinating. So reptiles can be kind of cool. And then, so yeah, we're going to kind of skip through some of this stuff, but again, our abdominal aorta, our descending aorta coming down here. What I should mention too is there's some arteries that are what we call paired arteries. Like obviously they'll have left and right. So that's, kind of what I mean by paired arteries. So the suprarenal arteries, renal arteries, gonadal arteries, and lumbar are all considered paired arteries. But then we've got superior mesenteric, celiac trunk, inferior phrenic, inferior mesenteric. All are non-paired arteries. So we've only got one. Okay. All right, down in the leg, structure of the blood vessels that go into our leg down here, kind of cool. And then the veins, right? So the structure of the veins is not really all that different from where the arteries are placed, right? If you do a dissection, if you guys end up getting to, take another anatomy class in the future, or if you guys are interested in pursuing this as a career, and later on in your educational path, you get to take a class, obviously post-COVID, that you'd be able to do an in-person lab with, and you get to do a dissection. Anytime you see an artery, you will see a vein, right? So the structure of all of these veins, there's generally going to be an artery right next to it. They're just not depicted here, obviously. That being said, there's some really cool physiological variance amongst individuals with relation to where arteries get placed, right? So obviously, so like John, you and I may have all the same, general places where we have arteries in our body, but the veins that we have might be in different locations, and we might not have as many veins, right? So depending on what we do, that can actually inform the development of veins in our body. So things like exercise activity can trigger vasculogenesis, or the creation of a blood vessel. It's pretty cool. So there's a lot more variation in venous structure and vein placement amongst individuals than there are in arteries. Another way that we say that is that arteries tend to be more conserved between individuals and veins are less so. Not to say that, like, John, you're going to not have a cephalic artery and then I have like 2 in my right arm. That's probably not the case, but just the placement of them. Like, so you may have like, a more reduced cephalic artery in your right arm than your left arm, and I might have, the opposite, but we'll still both have one. So it just kind of depends, but it's pretty cool. So I have this little blurb here on varicose veins and what they are. And again, this has to do a lot with, things like activity, being a sedentary individual. If you sit a lot all day and you have poor circulation in your extremities, then you can develop varicose veins where you have blood backflow into, structures or vessels that are it's usually in the legs. So the venous return isn't able to have enough smooth muscle force to be able to push the blood back through the veins back to the heart. So the cusps of the valves that prevent backflow don't have any ability to protect themselves and don't overlap. So this can lead to clots developing because blood is kind of lame, and if it ends up pooling or if it sits around, then thromboses will form. You can also get inflamed vessels called phlebitis, which can trigger inflammatory responses. It can trigger activity in the complement system, a whole bunch of stuff. You can actually also develop infections like gangrene, which some of you guys may have heard of. This, I might be dating myself here, but did anybody ever play the Oregon Trail in elementary school? Yeah. Oh, such a fun game. But there were times where some of your settlers or people in your caravan would get gangrene or dysentery. That was obviously, the classic. You have died of dysentery, right? But anyway, gangrene is typically a condition. It happens a lot with individuals who are bedridden or are paraplegic and are unable to walk around. It's really important to make sure that you massage limbs and maintain proper circulation, because if it pools, then you can develop varicose veins, and then you can get infections in the vessels that can lead to the development of anaerobic bacteria. It can cause gangrene, which will then, in worst case scenarios, can trigger a septic response in an individual. They can go into shock, and then you can die from that. You can also, other symptom of varicose veins is you can develop emboli. You can develop bubbles inside of your vessels, right? So if those bubbles travel to smaller arteries, if they get back into the heart, then they, if they get sent out through the systemic circuit, then they can, pass through smaller arteries and then cause them to rupture and then develop aneurysms that way. So varicose veins, typically not ideal. You can have them treated and you can get them corrected surgically. But if you have them, it's not a guarantee that you'll develop any of these. I'm not saying any of you guys do, or if you know people that have them, it's not a guarantee that you'll develop any of these. You're just at greater risk for developing these conditions. All right. So just as kind of a really quick example of where there's like some difference in nomenclature between arteries and veins. So the main artery that supplies blood to the head, so the outside of the cranium and then also the brain on the inside, is the carotid artery. We call it the common carotid, closer to the heart, but then as it goes into the skull, it's the internal carotid, and the branch that supplies the outside of the skull is the external carotid. We have a similar vein, or a homologous vein, that would be draining the brain and draining the face and the skull. That's what we call the jugular vein, right? So there are some instances where you'll encounter that, where you might, like, if you're in a bind and you only learned the names of the arteries, and you see this and you want to put carotid vein, that would be one of the few circumstances you would get that wrong. So we would call this the jugular vein. But if you guys go through here, you'll see a lot of similarities between the arteries and veins, right? So we're going to kind of breeze through these here. All right. There's some other flow charts. There's not as many for the veins, but you can definitely make these yourselves as a great study tool. All right. We'll take a quick drink here. How are we doing so far? Anybody have any questions? Doing okay on time, I think. All right, cool. So I'm going to give you your vocab word for the day: sphygmomanometer. Let me see if I can spell this right. I think I spelled that right. It's a fancy word for a blood pressure cuff, right? So, I don't know if I've already told this story, but I was definitely that kid when I was younger, and my mom would take me to CVS, the blood pressure machine. I'd always go over there and check my blood pressure, and I definitely broke it one day because I was just like pressing buttons and doing everything. But hey, I always knew what my blood pressure was, which was kind of cool. And at the time, I didn't really, think much of it. Um, but then, once I got older and I understood what high blood pressure meant and that, it runs in my family, I was like, oh, wow, that's something to definitely be concerned about. So how the heck does this thing work, right? So blood pressure cuffs are actually fairly simple. Really all it is it's a cuff that inflates with air. And the goal or the objective is to completely occlude or block off the arteries in your arm. All right. So once you've completely obstructed blood flow from the heart out to the forearm here, what you can then do is then apply a stethoscope, which allows you to hear very delicate, soft sounds inside the body. You can place that beyond our sphygmomanometer here, and then gradually decrease the pressure in the blood pressure cuff. So what will end up happening is as we reduce the pressure here, we end up getting to a point where we can have, if we're forcing blood through, what we would call our systolic pressure, then we end up opening the vessel on every time our heart is pumping blood out. So every time we've got that QRS complex, or ventricular depolarization, what we end up getting is our first, what we call Kortkoff sound. So this Kortkoff, Korotkoff sound. So that sound is the first bit, and that's what the physician or the clinician or whoever's taking your blood pressure or the machine at CVS will register as your systolic pressure. So systolic pressure, remember, if we're talking about ventricular systole, atrial systole, and then diastole, so the systolic pressure is the active force that the heart is exerting against the wall of the artery. So every time your ventricles are contracting and forcing blood out, that is your systolic pressure, okay? The diastolic pressure is where we have the passive force that just the structure of the artery with the pressure that's inside of our blood vessels at any given time is exerting on the walls of the artery, right? So just by virtue of there being blood inside of these vessels, and especially with arteries, we have passive pressure that's developed there, right? That is what our diastolic pressure is, okay? So as they gradually let the air out of the blood pressure cuff, the first sound that they hear is what we call the systolic blood pressure. So that first sound. And then when you can't hear any sound anymore, so the vessel is no longer occluded and you can't hear there being like turbulent flow basically, then once the vessel is completely open, that sound will disappear. And then we record that as the diastolic pressure. So that is our blood pressure. That's how we measure that. It's pretty, crude and barbaric, but it works, right? Like you literally just clamp it off and then gradually let the pressure go. You just measure when you can first hear it and then when you can't hear it anymore. So these values tend to vary, right, in terms of what healthy blood pressure is. But in general, as long as you're around like 110 to 120 over like 70 to 80, you're pretty good, right? There's, a very common heart condition called hypertension that affects most people in the United States. It's one of the, prime contributors to, being a precursor to heart disease. And again, heart disease can take on a bunch of different forms, but hypertension is one of the most deadly. And one of the reasons for that is because that hypertension means that the ventricles are overworking themselves. They are devoting way too much energy to force blood through your vessels. And a bunch of different things can contribute to that. One of the big causes of them, as they relate to blood vessels is actually going to be atherosclerosis. And so we'll talk about that a little bit later. But hypertension or high blood pressure affects a lot of people. Like I said, it runs in my family. So, I got to be careful about what I eat. Got to make sure that I exercise regularly and that I, take care of that part of my body because I'm more prone to developing it. So typically, like I said, so normal blood pressure, 120/80 or like 110/70, anywhere really within that range. And then you have a little bit of wiggle room outside of that as well. The one value that we're going to be measuring here that's going to change most in terms of magnitude is going to be our systolic pressure. And so typically, I mean, if you get outside of the normal range of both of these values, it's usually not good. But the more dangerous one, I would say, is going to be the systolic, because it's an indicator of hypertension and you're more at risk for immediate heart attack, right? So pre-hypertension or pre-hypertensive stage would be 139/89 or like 140/90. And then stage 1 is 140/159/90 to 99. And then stage 2 is 160/100. So, typically people who are in those like stage 1 or stage 2 are at risk for myocardial infarction, for an aneurysm, for a ruptured blood vessel, not good stuff, right? So if you have high blood pressure, it just makes sense. The heart is overworking itself. It's generating too much force for those vessels. And the vessels are only built to withstand so much pressure. They've got that normal operating range. And that's why our normal healthy blood pressure is around 120/80, because those are the pressures at which those vessels are in their best operating range and they're not being stressed too hard. All right. So as I've kind of already talked about some of these bits here, but so cardiac muscle hypertrophies, mostly the left ventricle. Again, if we're talking about hypertension here, if it's the systolic pressure, it's usually the left ventricle that's overworking itself. Can also increase risks of arterial or atherosclerosis, so increased chance of blood clots forming, leading to vessel rupture. Common conditions include cerebral hemorrhage, heart attack, renal hemorrhage, and retinal hemorrhage. So one of the ways that these can manifest is you can actually have ruptured blood vessels developing in the eye, which can be an indicator that you are, pre-hypertensive or, in a hypertensive state, right? If blood vessels end up rupturing in the eye. So you can also have bleeds inside of the kidneys as well, okay? All right, so this is kind of getting into what we had talked about at the beginning of the class, where we were talking about Tarantinoing our important message here. But we can measure something called mean arterial pressure or pulse pressure, where we essentially average our systolic and diastolic pressure, right? So our peaks and our troughs of our sine wave, right? So as the heart's working and relaxing, 120/80. So our mean arterial blood pressure should be around 100 millimeters of mercury. So what we notice along the x-axis here is we've got our different vessels where we've measured the pulse pressure in each of these vessels. So it makes sense that we have the greatest pulse pressure in the aorta. And then as we get farther away from the heart, the source of that pressure, the pressure drops, right? If you're standing right next to a speaker at a concert, it's probably going to be pretty loud. But if you're in the nosebleeds in the back, it's not going to be as loud as it is right in the front. You hope it is, because that would be an awesome show to go to. But the idea is like the sound isn't going to carry as far, right? Because you're not as close to the source of that force generation. But notice here that, again, as we get farther and farther away from the heart, we get into the arteries and the arterioles here. Once we get down to the capillaries, once we hit that capillary vessel, our blood pressure drops substantially. It actually drops most significantly between arteries and arterioles if you measure the slope of this, but it's huge, right? So this is, not to get like into physics or anything really, but if you guys are into physics, this will kind of make sense. But if you've got fluid moving through a tube or a vessel and you change the diameter of that vessel, it actually might be kind of counterintuitive, because if you're applying a constant pressure to that flow, then as you decrease the diameter of that vessel, you constrict it and the pressure should increase. But we're actually kind of seeing the opposite here. So as we get out into the capillaries, pressure drops essentially to zero here, right? So once we get down into our venules and we get past that capillary bed, then our blood pressure is essentially zero, right? So what things go into affecting mean arterial pressure? right? Well, mean arterial pressure is based around things like cardiac output and what we call peripheral resistance, okay? So the peripheral resistance of these vessels is really going to be the biggest factor, especially once we get into veins, that contributes to or determines our mean arterial pressure. Because cardiac output is just heart rate times stroke volume. So how much blood are you putting out and at what rate are you doing that? That's our cardiac output. That combined with peripheral resistance is what determines our mean arterial pressure, right? So it makes total sense that the mean arterial pressure is going to be much higher in our elastic and muscular arteries because they have the most peripheral resistance of the vessels that we have in our body. As we get farther away, we get out into our arterioles, our capillaries, veins, and venules. If you look at the tunica adventitia and the tunica media surrounding those vessels, it's severely reduced compared to the arteries, muscular arteries, and the elastic arteries of our body. So that peripheral resistance is a very, very small number once we get out here to, those structures, right? So kind of tying that all up together, one of the reasons why we don't have essentially any blood pressure in the venules, veins, and vena cava of our body is because the heart rate and stroke volume that far away from the initial source of the force production, the heart rate and stroke volume are still the same, but the peripheral resistance is so small that it essentially equates to nothing, right? So kind of cool. All about peripheral resistance, structure of the vessel. Okay, so here we've got a couple of different places that you can measure things like your pulse pressure or just your pulse if you wanted to. Some of the more common ones that we're all probably aware of are things like the radial pulse and the common carotid pulse. But depending on the patient, sometimes you have patients that have weak peripheral flow of blood out to their bodies. So sometimes you might need to, take a pulse on the femoral artery or on the axillary artery. You can measure pulse on the superficial temporal artery or even the facial artery on the mandible. You can measure pulse in a bunch of different places, right? So depending on the patient or depending on, who they are, like if you, like, let's say, first aid scenario, you come across a downed individual, they are face down, they're unconscious. You don't want to move them because you're afraid of like a spinal cord injury, but you're able to see or access the back of their knee. And in order to, check their pulse, you can measure their popliteal pulse if necessary, right? So there might be there's different scenarios for why that need may arise. Most of the time, you'll probably be able to do it in normal, pulse taking areas, but just in case you need to know, you can take pulse in a variety of different areas. All right. Another cool thing about blood flow in our body is this idea behind capillary exchange. So once we get down into our capillaries, so as we're forcing blood into these vessels, our pressure is going to drop substantially because we're constricting, we're changing the size of that vessel. All right. I think I might have misspoke before if I had said that pressure should increase. It should actually decrease because as you're forcing a fluid through that vessel, if you change the diameter, then you don't have as much surface area to work with. So you're unable to exert as much pressure on the walls of that vessel. So the pressure should drop that way. So if I said it otherwise, then I misspoke. I apologize for that. So how the heck are we going to actually exchange nutrients with our tissues if we have next to no mean arterial pressure here? Well, we still have some. We still have a little bit of blood pressure in the arterial end of the capillary bed. So a lot of the net fluid movement out of the capillary here is due to that pressure, right? Roughly 9/10 of the volume that we put out is due strictly to that arterial pressure. But let's say if we were, as we're pushing blood through our capillaries, and as we're exchanging all of those nutrients, again, we're also pushing fluid out of our capillary beds because it's just made of a single layer of endothelial cells. So, there's gaps and stuff that can form in there. So we're pushing water and plasma and stuff out into the extracellular space. If we did that all the time and we didn't get any of that back, then we would dehydrate ourselves with the construction of our circulatory system. We would lose all of our water to our interstitial space, and then we would bloat and inflate like a balloon, right? So one of the ways that we're able to retain fluid or essentially get it back from this process is all due to concentration gradients. Tying that back into the first bit of our class, those concentration gradients are controlling this. The first bit, it's just a pressure gradient. It's the same idea. We have more pressure in the artery, less pressure outside. Where's all the fluid going to go? It's going to go out of that vessel because we've got more pressure there. Now, instead of it being a pressure-related gradient on the venous end, instead it's an osmotic gradient. So the osmotic potential of our capillary bed is so low that we're able to essentially reabsorb 90% of the fluid that we excuse me, of the fluid that we lose due to arterial pressure on the arterial end of the capillary bed. So it's still a concentration gradient, except now instead of pressure, it's an osmotic gradient. So we've got more water outside, less water inside. So all of that water and fluid will move back in. I shouldn't say all, it's 90% of that fluid. So the other 10% ends up staying out here in the interstitial space. So don't forget that it passes into the capillaries, or I'm sorry, it passes into the lymphatic capillaries. That was meant to put the emphasis on lymphatic, not capillaries. We've been talking about capillaries this whole time. But lymphatic capillaries is important because the lymphatic system, as we'll find out, is not only going to be the main source of where most of our immune system operates and kind of takes place, but it's also going to be where we end up recycling some extra fat or adipose that can enter our circulatory system. It's also how we recycle roughly 10% of the fluid that we have in our body that escapes our arterial capillaries via that arterial pressure, right? So that we don't just kind of pool and develop fluid, in other parts of our body. All of that kind of gets recycled back through our lymphatic capillaries. So that 10% that doesn't come back there, right? So that's kind of cool. So we'll end up talking about that next Thursday once we get into the lymphatic system. So that'll be fun. All right. So as I mentioned before, we can contract or relax sphincters to allow for blood to essentially be redirected away from a particular capillary bed, right? So things like glucose, amino acids, and fatty acids can increase, concentrations, can trigger chemoreceptors that can then cause specific smooth muscle capillary sphincters to close off, right? The precapillary sphincters can also contract as carbon dioxide concentration decreases and our pH of our blood can increase, right? So we have all of these different things that can affect how our precapillary sphincters are operating. All right. So control blood flow. Let me see if there's anything I wanted to talk about here. Yeah, I mean, this is pretty much stuff that we mentioned before, but yeah, regulation of metabolic needs of tissues, increased carbon dioxide and decreased pH, or increased oxygen and nutrients such as glucose, amino acids, and fatty acids due to increased metabolism can cause a relaxation of precapillary sphincters and subsequent increase in blood flow through the capillaries if necessary. And then the opposite, so decreased carbon dioxide and increased pH, or increased oxygen nutrients such as glucose, amino acids, and fatty acids, can cause contractions of precapillary sphincters and subsequent decrease in blood flow through them, right? Regulation by nervous mechanisms. So increased physical activity or increased sympathetic activity can constrict blood vessels in the skin and viscera. So there's all these specialized areas where we can, depending on nervous system input, we can control whether or not those precapillary sphincters are relaxed or constricted, right? So increased body temperature, decreased body temperature, decrease in skin temperature below a critical value, anger or embarrassment, dilation of blood vessels of the skin, face, and upper thorax, right? So if anybody, like this happens to me sometimes, if I get nervous, like if, oh man, when I was defending my dissertation in grad school, my whole face was red. I was so nervous and anxious to get it over with, but my wife she'll get like a heat rash as well if she gets embarrassed. It's kind of funny. But yeah, so different nervous system input can control dilation of blood vessels and redirect blood flow to certain areas. Hormonal control, lots of different kinds of chemical activity as well. So increased physical activity, increased sympathetic activity, causing release of epinephrine and small amounts of norepinephrine from the adrenal medulla, constriction of blood vessels in skin and viscera, dilation of blood vessels in the skeletal and cardiac muscle, right? So we had talked about that at the beginning of class on how, certain hormones can cause constrictions in one areas and dilations in others. Long-term local blood flow, increased metabolic activity of tissues over a long period, as occurs in athletes who train regularly, can increase the number of capillaries. And then you can have decreased metabolic activity of tissues over a long period, as occurs during periods of reduced physical activity, where you can reduce the numbers of capillaries. I know I just kind of word vomited there. But this idea of vasculogenesis, or the development of blood vessels, is really interesting. And there's some neat stem cell pathways that determine where these structures develop, where we develop veins, where we can construct arteries or capillary beds. And so here, like what we're seeing is things like simply using an organ like muscle that we don't utilize or that we do utilize on a regular basis can directly control the number of blood vessels that are present there. And there's some really cool research that's going into how we can take kind of the body's ability to map this out and determine where we develop these things and use it for our understanding of how different vascular structures can develop in other areas of nature. One of my buddies is actually doing his PhD on vasculogenesis and how we can use this concept of vessel construction as a way to model and understand how cells can communicate extracellularly. So with like collagen interactions between them, it's way over my head, but it's, when he explains it, it's pretty cool. So, all right. So kind of just briefly going through some of these homeostatic mechanisms here. So regulation of the blood vessels. All of our blood vessels maintain their own diameter through what we call vasomotor tone. So we have typically a constant sympathetic nervous system stimulation of our blood vessels. So the arteries and veins, we can essentially change that tone by determining whether or not we increase or decrease the magnitude of that sympathetic activation. So if we increase that activation, then we can undergo vasoconstriction. If we relax that, then it undergoes vasodilation. But in general, all of our vessels in our body are under constant nervous input to maintain that vasomotor tone. All right. So a lot of these mechanisms you'll recognize from previous homeostatic mechanisms that we've discussed before, like for example, this baroreceptor pressure reflex, right? So we have specialized neurons that exist in different vessels throughout the body. We talked about some of them that exist on the arch of the aorta here. But again, so these arteries, essentially their job, not arteries, these neurons, their job is to sense changes in blood pressure, right? So one of the main ways that we can have drops in blood pressure is either through an injury, through loss of blood, or simple dehydration. If you haven't drank water at all today, go drink some water. You're probably dehydrated. And you're activating your sympathetic and parasympathetic nervous systems to increase things like adrenaline output, and also even cortisol output can be a result from this too. So Professor Beachco says drinking water can lower stress. It's science, right? But anyway, the point here is that these sensory neurons have feedback mechanisms into the medulla oblongata, into the cardioregulatory and vasomotor centers, which will then trigger outputs or sensory outputs into our sympathetic nervous system that directly innervates different parts of our arteries. And if blood pressure drops, then we constrict those vessels to maintain blood pressure. If blood pressure increases, then we can relax or we can tone down the amount of sympathetic input that we're putting there to reduce blood pressure, right? So it's this constant, delicate balance. But again, unless you're bleeding out right now, chances are if you have low blood pressure or if you're stressed, you might just be dehydrated. So increasing water intake can increase your blood pressure and help you out with that, right? So baroreceptor reflex can cause, if you're dehydrated, drops in blood pressure, then you can have, these different reflexes that can kick in to help, increase or decrease blood pressure, right? So let's see. So yeah, for example, blood pressure decreases, those baroreceptors in the carotid arteries and aorta can detect that increase. Cardiac regulatory center increases parasympathetic stimulation and decreases sympathetic stimulation of the heart. Vasomotor center decreases sympathetic stimulation of the blood vessels. One form of a baroreceptor reflex helps them dilate, right? All right. Chemoreceptor reflex. So again, depending on different chemicals that can be circulating in our blood, just taking on, for example, things like adrenaline and noradrenaline that can trigger, changes in blood flow or vasodilation or vasoconstriction. You can have, what was I going to say? Oh, pH, changes in the chemical environment related to pH, not even necessarily chemical signaling molecules. If your blood becomes too acidic or too alkaline, that can also trigger differences in our blood pressure as well, right? So chemoreceptors can monitor blood oxygen, carbon dioxide, and pH. And again, usually what you'll notice here, especially once we get into chapter 14 and we start talking about the respiratory system, we'll talk a little bit more about how the respiratory system, or how the content of carbon dioxide rather, will directly affect things like our blood pH. And a lot of that has to do with buffers that we make and things like that. It's pretty fascinating. Hey, get out of there. Sorry, my cat is being super needy today. So chemoreceptors monitor blood CO2 and pH, decrease blood oxygen, increase CO2, and decrease pH, decrease parasympathetic stimulation of the heart, which increases heart rate, right? So increases in carbon dioxide, causing things like hyperventilation, decreased blood oxygen, increased carbon dioxide, and decreased pH, increased sympathetic stimulation of the heart, which increases the heart rate and stroke volume. Because again, we've got too much carbon dioxide, we need to get this stuff out. That's what we want to do. Decreased blood oxygen, increased CO2, and decreased pH. Increased sympathetic stimulation of the blood vessels, which increases vasoconstriction. So we're able to increase blood pressure so that we're able to force blood through structures as efficiently as possible and help ventilate our blood and get that back into our lungs as quickly as possible. There's another mechanism we'll look at here in a minute that talks about the angiotensinogen pathway, which helps change and lower our or not lower, but actually increase our blood pH, right? Oops, here we go. So I've talked about adrenaline quite a bit, fairly self-explanatory, fight or flight, vasoconstriction in our intestines, in our viscera, vasodilation in things like our skeletal muscles. And so here we've got this really interesting pathway where if we have a decrease in blood pressure, we have that angiotensinogen to angiotensin pathway that I had mentioned before. So the kidneys can detect decreased blood pressure, resulting in increased renin secretion, which will then activate or convert angiotensinogen that gets released by the liver into angiotensin 1, right? So this enzyme will pass through the circulatory system and get up into the lungs, where in the lungs, we have this special enzyme called angiotensin converting enzyme, which converts 1 into 2, right? So 1 into 2, angiotensin 2 can then cause vasoconstriction to occur, help increase blood pressure, and then also stimulate the adrenal cortex to release aldosterone, which can then trigger the reabsorption of water in the kidneys to help decrease the urine volume that we have or increase urine concentration, right? So we can, if we're noticing that we're dehydrated and we have a drop in blood pressure, then we can utilize this pathway to make sure that we retain water in our kidneys so that we don't dehydrate ourselves even further. And then that fancy hormone, antidiuretic hormone, is pretty interesting. So again, depending on how dehydrated you are, which can be measured through either baroreceptors or chemoreceptors as well, can cause the kidneys to reabsorb water and create more concentrated, less dilute urine, right? Okay. So yeah, that's pretty much it. This is the figure that I wanted to show you guys about atherosclerosis. So this is the issue with plaque buildup inside or in between the endothelium and our tunica media right here. So you can see all of this plaque, this adipose tissue that builds up here can cause a bunch of different things to happen. One of the chief concerns being the reduction in the size of the inner lumen. Our inner diameter of our blood vessel here gets smaller, right? Not only that, but we can also see we've got ruptures in the wall of the vessel here. So the wall of the vessel becomes damaged as well. So if the vessel becomes damaged, then you can have plaque and adipose that can end up making their way into the circulatory system. You can have those clots and those bits of plaque travel, and they can obstruct other vessels in other parts of our bodies. So atherosclerosis, on top of the fact that it constricts blood flow in this given area, as the vessel begins to rupture and degrade, that plaque can then deteriorate and travel through the circulatory system elsewhere in the body.